Hello, and welcome back to the course. So we're looking at the residue theorem. So that's section 5.3, and we're looking at the first part of section 5.3. All right. So let's suppose that f has an isolated singularity at p. So it's a holomorphic function in a neighborhood of p, and we don't know if it's holomorphic at p or not, but it's just not defined at p, right? P is an isolated point. Now let's expand f in a Laurent series in some punctured neighborhood of p, so in some disk minus p, right? So we'll write it as a Laurent series like this, right? We know that we can always do that. So once we do that, then we notice that, well, all of these guys, if we look at each term separately, z minus p to the n, and n here varies over all integers, right? So z minus p to the n, that has a primitive in this punctured disk for all n except n is equal to minus 1, right? 1 over z minus p does not have a primitive there because the primitive would be a logarithm. It's not defined in the punctured disk, right? So we can essentially all the terms except the minus first term, so c sub minus 1, all the other terms don't really matter if we're going to integrate f around p, right? The only thing that's going to be left is c minus 1, right? C sub minus 1, right? So that's the only thing left after integration. So we'll call it the residue, right? It's what's left over. And so we'll give it a name. We'll call it, we'll come up with this notation, the res of f at p. It's the residue of f at p, and it's just the c minus first, so minus first c, guys, so c sub minus 1, so minus first coefficient in the Laurent series, right? So it's just that guy, right? That's what we mean by the residue. So if you have some function with some number of isolated singularities, you could just compute these by somehow computing the Laurent series here, right? Now for a small enough s, small go radius, so you can, if you go around go around this singularity, right, in a circle. Well, this was the formula for these coefficients, right, when we were developing the Laurent series. This is the formula for the c sub minus 1. It is just the integral of f, right? So, it's also this integral around a really small circle, right? Now, what this means is that via Cauchy, we can then basically relate any integral over any cycle to the residues that are inside, and that's what the residue theorem is. So we'll state and prove it right now, and it's basically just applying Cauchy's theorem. All right, so here's the theorem. So suppose that we have an open subset of C, we have finite subset S of U, right? And we have a gamma, which is a cycle. It's not supposed to, let's don't make it go through the isolated singularities, but it's a cycle in U that misses those singularities, right? So misses all the points of S, right? And we're going to assume it's homologous to 0 in U. And then we'll have this function with isolated singularities on the set S, right? So it's a holomorphic function, except maybe at these points S. So it's it's really a function with isolated singularities, function on U with isolated singularities in U, right? So then what we have is that the integral, well, we have to put the 1 over 2 pi I somewhere, so we're going to put it here. But basically the integral around gamma of f is equal to the sum over all the isolated singularities, and we multiply the residues and the winding numbers together, and we sum that, and that's what the integral is, right? So it gives us a way of computing the integral around any cycle as long as homologous to 0 in U by basically computing the residues, right? And so recall that homologous to 0 means that the winding number around anything in the complement of U is 0. So gamma does not wind around anything in the complement of U. That's all that we want. It could wind around points of S. Actually, it should. Otherwise, it's kind of boring. Otherwise, we just get 0, right? All right. So let's prove this. Sorry. So let's write S as this, right? So it's finitely many points, right? So I'm going to write them as W1 through WL, right? Now let R1 through R sub L be small enough numbers, really, really small numbers, such that all these disks, all these closed disks around W1 through WL are mutually disjoint. So I can, shrink these R's. I could even pick just one R, really, so that they're all mutually disjoint, right? So we have a little disk around each W, and small enough so that it doesn't contain, it's even the disks themselves don't butt up against each other, right? We also make sure that they are all, the closed disks themselves are all in U, right? So they're inside U, right? Including the boundary, right? And then we're going to define this cycle lambda, right, which is going to be gamma, and then we're going to subtract the right multiples of those little boundaries of those little disks, right? So if we have W1 here, right, this is the boundary of that little disk, right, and we're going to take the winding number of gamma around W1, and we're going to subtract, right? So we will actually go in the opposite direction, right? That multiple of the boundary, right? And we do that for every one of these, right? Now notice that in this picture, right, we have that the winding number of gamma around W1 is 1, right? It goes once around W1. It goes no times around this, right? I mean, around W2, right? Because it's just does this, right? So it doesn't wind at all around W2, and around W3, well, it actually goes twice around, right? W3, right? So these are the winding numbers over here, right? In this particular example picture. All right, so just recall what this is, what the lambda is. Now, the winding number, it's just an integral, right? And so we're integrating over lambda. That's just like integrating over gamma and all these guys separately, and multiplying those integrals by these guys. It's basically set up so that it's linear like this, right? So the winding number of lambda around P is, well, it's just the winding number of gamma around P minus, well, this was already, let me go here, right? I mean, this guy was already there, right? But so that's just the number that was in front of that integral, right? And then we integrated around this, right? That gave us the winding number of that little circle around W1, right? Sorry, around P, right? That little circle around W1, around P, winding number of that around P. Sorry. Right. So that's what this is, right? So now we want to you want to sort of see what that is for P. So you want to see what that is for P that are not in U and or they're in S, right? So basically what we're going to show is that lambda is homologous to 0 in U minus S, right? So if P is not in U, then the winding number of gamma around P is 0, right? Because it was homologous to 0 after all, right? So in U, right? So that's the so that's what we get. And because all these disks are completely inside U, right? So including the inside, right? Not just the circles, right? But including the inside. So like these circles, right, only go around what's inside those circles. And P is not in U, P is somewhere else, right? The inside is in U, right? So we also get that, all the winding numbers of these little circles around P are also 0, right? Now, if P is one of the points of S, then, I mean, this guy could be something, right? I mean, gamma can wind around P, might or might not, right? As we saw before. But if we look at, because all these little disks were disjoint, right? It's only one of them is gonna wind around this P, right? It's really, if P is W to the K, it's really W to the K, right? So that's one, right? But it's the only one. All the other ones are 0, right? Because, all of these disks, the closed disks, are disjoint, right? Now, what do these two statements mean? It means that the winding number of lambda around P is 0 whenever P is either not in U or in S, right? So basically, if P is not in U minus S, then the winding number of lambda around P is 0, right? In other words, lambda is homologous to 0, right? Right. All right. I was just worried there for a moment. Did I say lambda or gamma? I was getting those confused. All right. So if we now look at so now we basically trying to prove the theorem, right? So if we look at this integral, right, because lambda is homologous to 0 in U minus S, and it is a cycle in U minus S, by Cauchy's theorem, it is 0, right? So we have that's what that integral is. On the other hand, that integral, we'll write it out again as a bunch of integrals, right? It's the integral in gamma, right? I mean, there's always this 1 over 2 pi I in there, right? That has to be there. So this integral over here, and then, just by what lambda is, right? We get this expression over here, right? That's just the integral over that nonsense over there. So that's what we have. That's just what it is, right? And now we notice that this guy over here, that's precisely the formula for C sub minus 1, right? Which is what? Which is the residue, right? So, right. So that's the proof. That's exactly what it is. This thing is equal to this thing. Well, with the residues put in here, right? So that's it. So we have the residue theorem. So next time we'll look at how we use the residue theorem. I mean, it might be a little weird, that we're sort of, the formula that we have for the, for the residues for the c sub minus 1 is an integral formula, and we're going to say that we're going to solve integrals using this. The whole point is going to be basically, you can use this if you can figure out the residues in some other way, right? In some simpler way, right? Then you can use this to to compute integrals. All right, so that's all next time. So I'll see you then.